So we write this positron particle, 0, e plus 1. Very strange. It's a electron with a positive 1 charge. We'll talk about that in a second. And using our nuclear equations and our conservation of mass and charge, 0 plus 37 is 37. What number and a plus 1 gives me 19? Okay, that would be atomic number 18. And atomic number 18 is argon. So again, an example of natural transmutation, as all of these are. Potassium in these two examples naturally can transmutate into different compounds based on the particle given off. Notice this is a different radioisotope, K42, and this is K37. And knowing the radioisotope, knowing the exact isotope, both of these are potassium, same atomic number, different mass, they have different problems in their instability. Now, more importantly, what the heck is this positron? Well, it's a form of antimatter. And antimatter is supposedly from the theory of the Big Bang, where we have matter was made in two forms. And if the same antimatter hits the regular matter, well, this is the opposite form of an electron. When it collides with a proton, with an electron, it will annihilate each other and give off electromagnetic radiation. That's how a positron PET scan works. But let's look closely at what's going on here. So if you notice, what's going on here is the proton number is going up. All right. Well, I'm sorry, the proton number is going down. If you'll notice carefully here, we're going from 19 to 18. So in this case, a proton, all right, is emitting a positively charged tiny mass particle, positron. So it's losing its positive charge. Okay. So when it lost a little bit of its mass, tiny, tiny fraction, 2/1000ths of its mass, it took its entire charge away, and what you left is a neutron. So what this nucleus did, or this nuclei did, okay, you notice it has 37, okay, atomic mass, and this is 42. So this radioisotope has really two less neutrons. There's not enough neutrons in this nucleus. All right, now to get neutrons, you should be able to subtract here. 37 minus 19, okay, is what, 18? So this has got 18 neutrons, and this one, 42 minus 19, I believe, if my math is correct, is 21 neutrons. Check that, 23. I can do this simple math. So if you notice, this isotope has too less neutrons. So there's not enough neutrons to buffer the protons. Now we think that neutrons help the protons, okay, from repelling themselves. We know there's a strong force in the nucleus that keeps them together, but the neutrons help. So with two less neutrons, this nucleus is unstable, and probably these protons, all right, are repelling themselves in the nucleus. So to fix that, what the nucleus does is it increases its ratio of neutrons to protons. And one way to do that is for a proton to become a neutron. So notice 37 minus 19 is 18 neutrons here. Okay, if I do my math correctly, and I've been known to mess up very simple math here, this is 19 neutrons. And you may say, wow, it kind of gained a neutron. Well, it's 37 minus 18. It's a better ratio. So the neutron number definitely increased, and the proton number dropped because a proton became a neutron here. And that's what a positron decay is all about. It's all about fixing the nuclei of atoms that have too few neutrons to buffer the protons, and it makes it unstable. So the atom fixes itself and becomes more stable with a better proton to neutron ratio by doing that. Now over here we have the opposite. Okay, if you notice here, 42 minus 19 is 23 neutrons after my bad math, and over here, I think I can do this, I've got 22 neutrons. So in this problem, there's too many neutrons. So you have to have a correct neutron to proton ratio, so we think. So having too many neutrons, we have beta decay. And of course, in beta decay, a neutron, okay, gives off a high-speed electron, and a proton remains. So here, the atom fixed itself by what? Adjusting its proton to neutron ratio by what? Essentially, losing a neutron, okay, and converting it into a proton. So the proton number increased and the mass number, okay, of course stayed the same, but we changed a neutron into a proton. And the ratio of protons to neutrons in this case increased. And that satisfied this problem of this radioisotope. So radioisotopes that have too many neutrons, they lose them by giving off beta particles and becoming the proton numbers increasing, and lowering their neutron numbers do so by beta decay. And by positron decay, they do so by emitting this positron. And that, of course, increases the neutron number. So yeah, it's all about essentially what's inside the nucleus, and when they're made, what kind of problems they have. Now, these are few and far between on the reference table, but they are there. For atoms that are lower than atomic number 82, if they're radioisotopes, they are because of the wrong number of neutrons. But if they're beyond atomic number 83, okay, notice 27's below atomic number 83, so their problem is the neutron problem. In this case, too many, that's why it's beta decay. But in this case, beyond atomic number 83, this is going to give alpha decay because they have too many protons. So you can actually make some guesses of what kind of radioisotope, what kind of emission it gives off, whether it's alpha, beta, or positron, all right, based on the number of protons. If it's beyond atomic number 83, it's going to be an alpha to get rid of the extra protons that are making the nucleus unstable. Or if it's too low of a neutron number, you're going to give off positrons to make more neutrons. Or if it's too many, you're going to lose those neutrons by beta decay. Any case, probably too much information for writing nuclear equations, but I like to think that if you know a little bit more, it makes a lot more sense. But again, all these examples are natural transmutation. How do I know? There's only one reactant. Therefore, they naturally do this, and we cannot control them. And their half-lives, okay, are something that we just have to live with. We can't control these half-lives, but they do this on their own. If you had a second reactant, forcing them to collide to make this happen, that'd be unnatural or artificial transmutation.